So, and I'm going to talk about it on some of the slides here. Well, I'll have some of the projects, I should say. Uh, in the past, when we were collecting data, we were always collecting pretty much energy and timing of specific signals that occur in these detectors. However, since electronics is getting faster, right now they want to do, and the amount of data we can store is getting larger, they want us to do real-time waveform sampling. And that gives us a lot more information on what the waveform actually looked like, and it can help with the physics analysis. To do real-time analysis, so part of the problem is if you sample everything coming out of a detector, it's just going to be huge amounts of valuable data, and you can't do that. And we have to come up with a way of triggering, knowing what data we want to collect. So in the past, we have waveform, we have an analog front end that looks at a signal and goes over a certain threshold, sample the data, calculate the timing. It's really easy using analog circuitry to pretty much do a peak finder and get accurate timing, sample that, send it out, digitize that 2 pieces of data, send that over system. Waveform sampling, on the other hand, now you got to put that into the FP, so now you need to have some sort of digital logic to sample the waveform. There's a lot of complexity on, you need to have enough memory to record the waveforms, how many samples do you need, pre-samples, post-samples, how many the total number of samples you want to collect. So it's just a lot more information that you have to do at the very front end to look at the data to see if you want to collect the data and then transmit that up to the final data form. So having the mechanism to look at those front end information using a machine learning algorithm, which is going to give us real time feedback saying, yes, this is something that we're interested in, collect that one waveform and send it back. It's something that we think is going to be very useful, and it's just going to reduce the overall data set. I'm skipping over a lot here. I'm trying to minimize it, but yeah. So that's one thing that we're looking into. But
I mean, I have questions, but should I just wait till after your presentation?
yeah. So pretty much what I'm going to be talking about, I'm just going to list just a few projects that my group is working on. Very little detail, but just to show you that we're working on quite a few different projects. So,
Hi.
And before you start, this is our advisor, Dr. Michaela Mu.
Hi.
hello. All right, so I don't think I introduced myself actually. So I'm Jack Fried. I'm the DAQ group leader here. I have 5 members in my group, including Jillian Donahue. She's one of the newest members of the group. But she's doing great work here. So, and actually, I think one of the film Lori is actually in here.
Oh,
We can
okay,
talk about it. So, primarily, my group, what we do is we develop the hardware, software, firmware that are used in quite a few different experiments here at VNL. And actually abroad, some of the electronics we develop is installed in experimental neutron source in Australia. Some places, I have some of my electronics at CERN, Oak Ridge. So we collaborate with quite a few people, different groups around the world. So most of these projects I'm going to show you, it's pretty much fully developed here at Instrumentation.
In addition to stuff that goes into the RIC and stuff, because there's a lot of stuff.
Right. So we do a
on
lot.
site.
Exactly. We do a lot of stuff here in house as well.
The RIC is it's the big collider that we have on site, which is I think the only other particle ion collider other than the large hadron collider at CERN.
Okay. So here's so this is a project that we've been working on here very recently. It's a thallium bromide detector. So so this detector, and actually I'll walk you around. You'll actually see this. So this is actually a gamma detector, so it detects gammas. Normally, I don't know if anybody mentioned to you that normally the medium it used to detect gammas is CZT. Phthalate bromide is a new material that we're trying to see if we can use it in a detector. It's very difficult to use it because the growing phthalate bromide crystals have a lot of imperfections. So the data coming from it is not very clear. So we can't. So one of the scientists here came up with a concept of using a Frisch grid, which allows us to use 3D correction of when the gammas interact with the phthalate bromide. So pretty much what happens is, if there's an imperfection in the crystal, when the gamma interacts with phthalate bromide, you have the charge which drifts. We have pads on the side of the crystal, so we can actually see where inside the crystal the interaction occurred. And so we can see the location in the X and Y. The Z-axis is given by the anode and cathode. So with the 3D, once we know where that interaction occurred, we can actually make a correction file. And so with a source, and this way we can use the phthalate bromide to give us an accurate result on the energy being deposited inside that phthalate bromide crystal. So here we developed, so my group developed this readout board, which is using a Kintex 7 FPGA. It has 64 channels running at up to 80 megasamples per second. I think in this case we're only running at 10 megasamples per second. So it's two ADCs connected to a FPGA using, I don't know if you guys are familiar with the JESB 204 standard. It's a high-speed data link using transceivers. It's a self-trigger readout. It self-triggers on each channel. It can also trigger on neighboring channels. So it's a cute little package. You'll see this when I take you on a tour. And the whole, all the ADCs are being read out over Gigabit Ethernet. So this little detector is supposed to be a handheld device, which we're working with a company called Bubble Tech Industries. So this is the case we're working with a commercial partner. And so this is a small board used to read out the phthalate bromide detector, and it utilizes one of the ASICs, the AVG ASIC. I don't know if they talked about that here.
We've seen it on the poster in the labs.
Okay. So this is actually AVG 3 Dev ASIC. Mm-hmm. So the system uses that ASIC combined with the ADCs going into the FPGA. FPGA does all the triggering and it reads out the system. And I can, like I said, I can show you a demo. And you can see here, here's the detector, this filter box, and you can see the quarter here. So it's actually relatively small. So the idea is to have this as a handheld unit, which is going to be walked around and to look at for radiation sources around. So have you guys heard about Dune at all?
Yes.
Yeah.
Okay. So did you see the APA or any of the boards or just the ASICs?
I believe just the ASICs.
Okay. So
Do you want to explain to them what Dune is? Because people consistently say, hey, this is for Dune. Hey, we're doing this for Dune. I'm not actually sure they know what like the actual experiment is.
okay.
They do know the acronym.
Okay, so Dune is actually a really, really, really cool experiment. So currently we're working on Proto Dune, but the final Dune experiment, what it is, it's a neutrino. So it's a so Dune stands for Deep Underground Neutrino Experiment. And what they're doing is they're going to be generating neutrinos at Fermilab in Chicago. They're going to be shooting these neutrinos through the Earth's crust, pointing it to a mine in South Dakota.
That's tough.
And the detector in South Dakota is going to pick up these neutrinos being generated. Now, they're shooting, I don't even know how many billions of neutrinos, but out of those billions of neutrinos, only a few, maybe one or two will be detected I'm not a physicist. I don't remember the rate, but it's incredibly small. I mean, maybe 1 or 2 a day, if that, or something. Could be wrong with that, but it's insane. Yeah. So the reason behind doing this is they want to study, I believe, the concept of asymmetry, where they're trying to figure out why they're so. Again, not 100% sure. This is I designed the electronics. I designed it. When it comes to the physics, I'm not the best person to ask. But I believe what they're trying to figure out is to understand why there's so much. So you have so you know what antimatter is, right?
Yes.
So they're trying to figure out the asymmetry. Why is there so there should be theoretically after the Big Bang there should be standard matter and antimatter. There should be an equal amount. But why is there almost no, well, there is no antimatter pretty much around us. So they're trying to use this experiment to figure that out, I believe. So they're trying to figure out the asymmetry. So that's one of the big questions in physics. So that's what this experiment is for. I believe. So for the Dune experiment, when it comes to the electronics, BNL was responsible for what is known as the cold electronics. The cold electronics starts from. So, did they explain to you how the electronics works? Did they talked about the liquid